order. Yeah, again, so if you have any question, okay, just type in the chat window, okay. So yeah, we do this one first, okay. So yeah, because the couple of students asked me the assignment of the RS, okay, to the Fisher projection, okay. Some students kind of we didn't do too much practice for it, okay. So yeah, we do this one, okay. Other should be easy, okay. Newman projection we talk about many times, okay, and then also the ring structure, okay. Okay, so for the Fisher projection, okay, so yeah, first thing you need to understand, okay, so yeah, all the horizontal bond actually point towards you, okay, and then vertical bond actually point away from you, okay, and then yeah, if it's hard for you to memorize the case, so yeah, you can draw the horizontal bond at the wedge, okay, so like this, okay, so that's help you kind of a little bit get idea, okay, right, and then yeah. We'll align RS for these two stair centers, okay, one by one, okay. Okay, so for the top one, okay, so yeah, this one, okay, so yeah, the highest one definitely OH group, okay, so that's one, okay. And then the hard thing come to the which one is kind of the second part, okay, so yeah, we have a top branch and a bottom branch, okay. The top branch, okay, this carbon has two hydrogen, one oxygen connect to it, okay. And then for this carbon, okay, one hydrogen, one carbon, one oxygen, okay, so that means the bottom one has high part, okay, because this one has one actual high carbon, okay. 2 and then 3, okay. All right, so then you draw the RK from 1 to 2, okay, and then 2 to 3, okay. So that looks like the counterclockwise, okay, but the hydrogen, okay, so the lowest party group point towards you, okay. So you need to give opposite assignment, okay, so that should be R, okay, so for this there's it. Right, and then I use another color pen, okay. For the bottom one, okay, we do the similar thing, okay. Bottom one, okay, so we have the highest priority one is kind of oxygen again, okay, so we have the OH group, okay, so that's one, okay. Right, and then we have two branches, one kind of connect with aldehyde carbon is you treat as the two oxygen, one hydrogen, okay, because CO amount treat as two CO, okay. And then go up, okay, so yeah, one oxygen, one carbon, one hydrogen, okay. Definitely this one kind of higher priority because this one has two oxygen connected, okay, so that's 2 and then 3. Right, draw the arc 1 to 2, 2 to 3, okay. So looks like a counterclockwise, okay, but again, okay, so this time you have the hydrogen point towards you, okay, and you need to give opposite alignment, okay. And it looks like clockwise, okay, but you need to give opposite alignment, okay. So that's be S, okay. Yeah, so that's S. Yeah, so that's how do you do the assignment for the Fisher projection, okay. Right, so next kind of the naming question, okay. So yeah, this one kind of relatively hard one because you have to redraw the reaction, the formula, okay, several times, okay. So yeah, that's right, okay. So yeah, for the Fisher projection, okay, always the point towards you, okay. For Fisher projection, some people also call the Fisher bone, okay. So yeah, where it's kind of Fisher bone, okay, like or the fish, okay. Yeah, like Fisher bone, okay. So Fisher projection, okay. So always the point towards you, the wedge bond, okay. So I mean the horizontal bond, okay. So that's the keep in mind, okay. So that's key thing, okay. Right, and then next we do this naming question, okay. So that's also not easy one, okay. So if I give you a name and then ask you draw the structure, okay. So you do it kind of backward, okay. So don't worry about kind of the attachment and those stair capture, okay. We do the octane 3 5 ion, okay. So the 8 carbons, okay. One, two, three, four, five, six, seven, 8. Okay, 8 carbons, okay. Right, and then you can number it, okay. So it doesn't matter which way do you want the number, okay. So from left to right, okay. 1, 2, 3, 4, 5, 6, 7, 8. All right, okay. So yeah, 3 in, okay. So that means double bond between the third carbon, fourth carbon, and 5 ion, okay. So means the triple bond between the fourth and fifth and sixth carbons, okay. But keep in mind, okay, triple bond, okay. So we need the show 180 degrees, okay. So in this case, we have to kind of redraw it, okay. So that's you need to get kind of the eraser and also pencil, okay. All right, okay, so triple bond, okay, so yeah, 180 degrees. All right, so that's still 5, 6, 7, 8. All right, okay. Next, kind of we add a prefix, okay, so the two, ethoxy, okay. All right, okay. So now we come to the stereochemistry, okay, stereochemistry, okay, so we have that bond, okay, so that's here showed you the Z, okay. So Z means here the cis, okay, so but here we draw the trans, okay, so that means here unfortunately we have to redraw it again, okay. We need to bring this branch down, okay, so give you cis, that's also kind of here Z, okay. Okay, so that's the pretty much kind of the right stereochemistry for the theta bond, okay. All right, okay, and then we take off here the RS, okay. So that's some kind of tips for you guys. I already showed in the class, okay, in the discussion, okay. So if it's RS assignment, okay, don't worry about, okay. So very beginning, just draw straight line, okay, and then you go ahead and then RS, okay. So if come up same assignment, okay. So ask the question, okay. So that's we call kind of just change the bond to wedge, okay. If come out opposite, okay, and then you change it to the dash, okay. Right here, okay. So that's here the ethoxide highest priority, okay, and then followed by this branch, okay, because this branch has more carbon and this branch, okay. So looks like here the counterclockwise, okay, okay. So the here show you R, okay. So that means here this opposite here from the question kind of the right. Then we need give the dash line. Yeah. Right. So that's the full structure for this molecule. And so actually there are other way to draw it. Okay, for example, okay, that's here. Okay. So actually if you flip this molecule like 180 degrees, okay, and then that's the ethoxy will become the wedge. Okay. So in other words, the wedge dash doesn't matter. Okay. So more important, you give you right stereochemistry. Okay. So and so that's something to keep in mind. Okay. Yeah. Right, so that's a relative hard one, okay, and then we move to a last naming question, okay. Yeah, if you guys have any question, okay, so put in the chat window, okay. So right. So for last one, okay, so it's a give you structure, ask you name it, okay. So again, you don't need to worry about the stereochemistry, okay. So we just kind of name it as a regular molecule, okay. So first find the highest priority group, okay. Highest priority group, okay, for this one, okay, so that's definitely considered about, okay, all the bromine and the methyl, just the prefix, okay. And then you need to find the longest carbon chain contain both of the carbon of your theta bond, okay. So longest carbon chain, definitely this one. Yeah, that's the longest carbon chain, okay. All right, okay, and then that should be 5 carbons, okay. So we try to number this carbon chain, okay. So we try to give theta bond lower number possible. That's why we do it kind of from right to left. Okay, 1, 2, 3, 4, 5. Okay, all right. So this compound we should name as the pentene. Okay. All right, and then we need to give also location number for the theta bond case. That's 2 pentene. You put 2 between T and E. That's also fine. Okay. All right, and then we take off the 3 substitute group. Okay, so the bromine, methyl, okay. So put them alphabetic order before the partner name, okay. So that's it should be 2, 4 dibromo and then 3 methyl, okay. Dibromo. Oh, 3 methyl. Almost no space, okay, and then 2 high, okay. 2, 4 dibromo, 3 methyl, 2 pentene, okay. Right, so no done yet, okay. So no done yet, okay. So we have theta bond, okay, and also the steric center in the molecule, okay. So we have to design RS, okay. And for the theta bond, okay, so the high priority group, okay, so it's here and here, okay. So that's on opposite side of the bond, okay. So that means theta bond, we need to give E, okay. So and giga. All right, and then for the steric center, okay, so that's not hard, okay. So highest one is bromine, and then followed by this branch, okay, because this branch has more carbon, and then followed by this methyl, okay. So 1, 2, 2, 2, 2, 4, okay, because the hydrogen point away from you, okay. So you just kind of consistent assignment, okay. So clockwise it should be R, okay. right? And then put in the parentheses and link with full name. Okay? So that's here the full name for this molecule. Okay, and you don't need give location number for theta bond and also the cell center because it's just only one. Okay, but here the exam quiz. Okay, so if you give the kind of location number, that's be okay. Okay, so you want to lose the point. Okay. All right. Okay. So that's we done the chapter 7. Any questions? Right. So I already upload one the worksheet. Okay. So for tomorrow kind of discussion. Okay. So online, and please work on it. Okay. So that's pretty good worksheet. Okay. And then you can have some little bit idea. Okay. What kind of question you'll see in exam 2. Okay. All right. So. Yeah, so this node chiral carbon, this is node chiral carbon, okay? Chiral carbon has be 4 different attachments, okay? So this one just 3, only 3, okay? So yeah. So no RS for the okay, chiral carbon, okay, has be tetrahedron carbon, 4 different attachment, okay? Yeah, like this, okay? So now be kind of sp2 hybridized carbon, okay? Those sp2 hybridized carbon, okay? All right, any other questions? All right, so if there's no further questions, okay, so we'll start a new chapter, okay, chapter 13, okay. All right, so we'll totally switch the gear, okay, because so now we switch from stereochemistry to spectroscopy, okay. So when you have one organic compound at hand, okay, so how do you figure out this the structures, okay, and how do you kind of figure out this is the ethanol, this is kind of alcohol, okay, whatever, okay. And so we will use some kind of more advanced way, okay? So that's called spectroscopy, okay? So in old time, okay, so so far we just use melting point, boiling point, okay? That's cannot kind of figure out the structure of a molecule at least, okay? But the spectroscopy, okay, so help you try to identify what structure and also distinguish between molecule, okay? So what's spectroscopy, okay? Spectroscopy is just kind of electromagnetic radiation interaction with the study interaction between electromagnetic radiation with the molecule. Okay. Just electromagnetic radiation and then interact with the molecule. And so if you strike here electromagnetic radiation to some kind of molecule, and then you generate kind of a spectrum, okay, and then you from this spectrum you get information what's the structure of molecule, okay. So we'll spend 3 chapters, okay, study 3 different spectroscopy, okay. Chapter 13 we'll study kind of infrared kind of spectroscopy. Chapter 14 okay, study nucleus magnetic resonance the spectroscopy called NMR, okay. And also the chapter 15 will start the UV the spectroscopy. So because before we talk about kind of the spectroscopy, we first a little bit about the basic knowledge about the electron magnetic radiation. Okay, so electromagnetic radiation just just everywhere. Okay, so we travel at the constant velocity. There are many different types of electromagnetic radiation. Okay, so like the sunlight actually is one kind of electromagnetic radiation. Like our cell phone kind of signals, okay, also a kind of magnetic radiation. Okay, and so for all the electromagnetic radiation can actually travel at the same the speed, okay, same velocity, okay. So this speed is kind of the velocity of the light, okay. So that's 3 times kind of 10 to 8 meter per second. Okay. All right, and although they have same speed, but they have different wavelengths and also the frequency, okay. So wavelength is the distance between the 2 consecutive identical points on a wave. Okay, so for example, from here to here, or from here to here, or from here to here. So that's we can also count as one wave. Okay, and then the length, just kind of wavelength. Okay, Frequency just kind of the how many full circle for the wave pass through a point at 1 second. So the times kind of 1 second and report as hertz. So and so if you time the wavelength with frequency, that's give you the velocity of the electromagnetic radiations. Okay, times kind of wavelengths. Okay. Yeah, so lambda we know that kind of the wavelength. And the mu, okay, so this one we call the mu, okay, that's the frequency, okay. So the units hertz, okay. Right, so because this is constant, okay, so based on this formula, okay, easy to understand, okay, so if we have kind of the longer wavelengths, okay, and then the kind of longer wavelengths, and then we will have kind of the higher frequency, okay, so let's do this, okay, so so these two kind of the reverse relationship, okay, so long wavelengths, lower frequency, longer wavelengths, lower frequency, okay. So on the other hand, okay, so if you have the shorter wavelengths, okay, and then high frequency, okay, that's also shown here, okay, so the top one, low frequency, okay, and then long wavelengths, okay, bottom one, high frequency and then low wavelengths, okay. Right, and then for different electromagnetic radiation, they also have different energy, okay. So that's also showed on the screen, okay. So energy can be calculated by this formula, okay. So H times mu, okay. Mu is the frequency, we already know that, and H is Planck constant, okay. So that's just constant, okay. So and we already know there's that's relationship between the wavelengths and also the frequency, okay. So that's case, okay. So we can change the frequency to C divided by kind of the wavelengths, okay. So that's same thing, okay. All right, so based on this formula, okay, so also can easily understand, okay. So if we have kind of the higher frequency, okay, so higher frequency, okay, and then we'll have kind of higher energy, okay. So higher frequency, higher energy. Right, and then but for the wavelengths, okay, so if you be in the inversely kind of proportional relationship with the energy, okay. So if you have the longer wavelengths, okay, and then you will have kind of the lower energy, okay. So those relationship which please make sure you keep in mind, okay. Right, so there are many types of different electromagnetic radiations. Okay, here just quickly go through them, kind of very nice the figures. Okay, so we from the high energy, high frequency, and also short wavelength one. Okay, so gamma ray. Okay, so gamma ray. Okay, so the wavelength only about 10 to minus 13 meters. Okay, so that's the size of pretty much close to atomic nucleus. Okay, so gamma ray has very high energy, okay. So you don't want to mess up with gamma ray, okay. So that's kind of huge damage, okay, to your body, okay. And then next one is the X-ray, okay. So X-ray, okay, so the size about the 10 to minus 10, okay. So that's close to the atomic kind of the atom kind of size, okay. And also very high energy, okay. So that's why we go to the hospital, people take some kind of the doctor takes some kind of X-ray image for you, okay. So very high the energy can pass through your skin and also tissues, okay. All right, and then next the ultraviolet, okay. So UV kind of the range, okay. So UV range wavelength about the 10 to minus 8 to 10 to minus 9, okay. So that's the close to size of molecules, okay. And then next kind of visible kind of range, okay. Visible range kind of just about 10 to minus 6 to 10 to minus 7, okay. So that's the size of the bacteria or maybe kind of a virus, okay. And then next kind of into the infrared, okay. Infrared, okay. So the wavelength is about 10 to minus 4 to 10 to minus 6 meters, okay. Right, and then further increase the wavelength, okay, that's come kind of microwave, okay. Microwave, we have the size kind of probably to some kind of object, okay, so we can see kind of by our eyes, okay. And but yeah, the loss energy should be kind of radio frequency, okay? Radio kind of low radio kind of radiation, okay? Radio kind of the radiation kind of the wavelength about kind of hundreds meters, okay? So that's the much kind of a long wavelength, okay? Yeah, so that's the please the keep in mind, okay? And for our human eyes, okay, so we cannot detect all these electromagnetic radiations, okay, so only very narrow range kind of the visible range, okay. So from 400 nanometer to about 720 nanometers, okay. But that's already give our very colorful kind of world, okay, so we can see all different colors, okay. For some kind of the animals, okay, so like maybe the cats or something, okay, so can detect kind of the ultraviolet, okay, or maybe some kind of the infrared kind of regions, okay. And for you guys, okay, so just try to remember their kind of wavelength rank, okay, so, or maybe kind of frequency rank, okay. So the last frequency is radio, okay, and then followed by microwave, okay, and then followed by infrared, okay. So infrared, okay, so I label as kind of IR, okay, so, and then followed by variable kind of region, okay, so and then followed by kind of ultraviolet, okay, so label as kind of UV. Right, and then next is the gamma ray, X-ray, and also gamma ray, okay. Yeah, so that's there kind of the wavelength kind of long ranking, okay. So the frequency ranking is just kind of reverse order, okay, because we have this kind of relationship, okay. And the same thing for the energy, okay. So energy kind of the same order as the frequency, okay. Yeah, make sure the understand this the order, and then I may test in the future exam question, okay. Maybe ask you kind of ranking question, okay. So can put this kind of rank, okay. And so for the organic chemistry, okay, so we only focus on the three electromagnetic radiation. One's kind of radio, okay, and then one's IR, and then next one kind of UV, okay, kind of here, okay. And in chapter 13, okay, so we'll study kind of the IR spectroscopy, okay, and then in chapter 14 we'll study NMR. NMR actually kind of based on radio frequency, radio kind of radiation, okay. And chapter 15 we'll study UV spectroscopy. Okay. All right, and then here's kind of just some definitions. Okay, spectroscopy study interaction of electromagnetic radiation with molecule, okay. And then spectrum, okay, so a plot of the amount of the electromagnetic radiation, okay, absorbed or emit, okay, versus kind of frequency or wavelength, okay. So what's that mean, okay? So I'll draw you two spectrum, kind of, you know what I mean, okay. Right. Okay, so so normally speaking, molecule kind of stay at the we call the ground state, okay. So this ground state can be just the bond, or maybe kind of nuclear spin, or maybe some kind of electron kind of and then there's higher energy level we call the excited state, okay. Right, okay. So normally speaking, kind of you stay at kind of ground state, okay. And then there's the energy gap between the ground state and those excited state, okay. There's the E. Okay. Right, and then if you try to strike this molecule, maybe kind of the atom or kind of electrons, okay, by some the electron the magnetic radiation, okay. So if the frequency of this electromagnetic radiation, okay, match the energy gap between the ground state and also the excited state, okay. So we know that the H mu, okay, equals kind of the delta E, okay. So if this energy, okay, so of the electromagnetic radiation match the ground state and also the energy gap between ground state and also the excited state, okay. And then this molecule will absorb this electromagnetic radiation, and then the jump to the ground state, jump to excited state, okay. So that will generate the absorption spectrum, okay. So it's absorb some electromagnetic radiations. Okay, so some certain wavelengths. Okay, right. So for the absorption kind of spectroscopy. Okay, so something like this. Okay, so y-axis. Okay, so normally just the absorption. Okay, and then here's the 100%. Here's the 0%. Okay. And the x-axis, okay, so just wavelength, okay, so right, and so normally kind of scan the sample with the different wavelengths of the electromagnetic radiation, okay. So if there's no absorption, okay, so that's kind of just 100% kind of pass through, okay, so no absorption, okay. But if there's the energy, okay, match the energy gap between excited state and then also ground state, okay, then you have kind of absorption, okay, something like this, okay. Yeah, and you generate the absorption spectroscopy, okay. Right, so next come to kind of emission the spectroscopy. What happens kind of once some the molecule absorbs the energy, jump to kind of excited state, okay, so it won't stay there forever because that's kind of extremely unstable, okay. And then it will go back to its original kind of ground state, okay. So when it go back, it will release energy, okay. So this released energy will showed as the electromagnetic radiation, okay. Right, so that we use h mu prime, okay, h mu prime, okay. Right, and then when it's released, okay, so if you have some detector, okay, by your sample, okay, it's can detect what kind of frequency, what kind of wavelength of the released energy, okay, and then you can draw the kind of emission the spectroscopy, okay. So emission spectrum, okay. So that's emission spectrum, okay. So for emission spectrum, okay, so normally the y-axis kind of intensity, okay, so that's how strong of your the emission, okay, and x-axis still just the lambda, okay, right? So so normally speaking, kind of you should see something like this, okay, so some signal, okay, so here kind of very strong signal, okay, so that means emission kind of quite strong, electromagnetic radiations, okay, okay, and then for our class, okay, so the IR and the UAVs, okay. So that belongs to kind of absorption spectroscopy, okay. And for the NMR, okay, also it belongs kind of emission spectroscopy, okay. So that's the little bit keep in mind, okay. So and so here's kind of a little bit the outline, okay. So what kind of the information can provide by individual spectroscopy, okay. So for NMR, okay, so it's just the radio frequency, okay, so radio wavelength, okay, so pretty low energy, okay. So this energy can only change the spin of your nucleus, okay, so and then can provide the information about what kind of carbon, what kind of hydrogen in the molecule, okay, very useful, okay. And then infrared, okay, so relative high energy, okay, so and then shorter wavelength, okay, so this energy can match the bound vibration energy, okay, so polar bound vibration, okay, and then can provide information about the function, okay, like there's a aldehyde this molecule or kind of there's alcohol in the molecule, okay, acid in the molecule, okay. And for the UVs, okay, so energy kind of further increased, okay, so this energy can promoted the valence electrons in the valence shell, okay, so to the higher kind of the energy level, okay, statistic, okay. So very useful, provide information about the conjugated pi bond system, okay, so and so far you don't need to understand what's going on, okay, just keep a little bit idea, okay, so once we done the all three chapters, okay, we'll come back, you can get a little bit better idea what's going on, okay, for the all three kind of spectroscopy, okay. Right, so now we can focus on kind of IR, okay, so get a new page. All right, okay. So for IR cases here, the IR energy can match the vibration energy level of your covalent bond, okay, so and then yeah, provide information about here the functional group. Okay, that's we already know that. Okay, and so yeah, for vibrational IR wavelength. Okay, so yeah, it's yeah from 2.5 times yeah the 10 to minus 6 meter to 2.5 times 10 to minus 5 okay so meters. Okay, so those here the yeah actually IR range kind of much broader than this. Okay, but here the only this range of IR can yeah the yeah match energy of the bound vibration. Okay, so that's why we choose this range. Okay, but yeah, if you see kind of yeah those numbers are quite small. Okay, and also yeah not easy to yeah the recorded. Okay, so yeah 2.5 times 10 to minus 6 meter. Okay, so in this case yeah people change the yeah units of the yeah IRK to yeah frequency. Okay, but yeah they don't use kind of just yeah the mu. Okay, so you use yeah the units yeah the we call kind of yeah wave numbers. Okay, so yeah that's yeah a little bit yeah different from yeah the frequency. Okay, so yeah actually kind of same thing, but yeah the yeah different way to yeah the yeah record yeah the frequency. Okay, wave number. So wave numbers, okay, so yeah, people use yeah mu, okay, still use the mu, but yeah, some kind of yeah, yeah, a little bit curve on top of it. But sometimes yeah, people just kind of put straight line. That's the same thing, okay, right? And the wave number indicated how many the waves in 1 centimeter, okay, right? So that's 1 centimeter, and then here's kind of wavelength, okay. So 1 centimeter divided by kind of yeah wavelength, that's actually kind of yeah give you kind of yeah the wave number, okay. And so yeah, actually kind of treat it as the yeah wave frequency. That will be fine. Okay, yeah, that will be fine. Just the little bit different. So frequency. Okay, so yeah, we know that kind of the yeah. It's mu. Okay, so that's the how many wave. Okay, in 1 second. Okay, 1 second. Okay, so that's wave numbers. How many waves? Okay, in 1 centimeters. Okay, so that's the yeah some little bit difference. Okay. Right. So if we use wave numbers, okay, we can yeah, you can do some kind of math, okay, convert kind of yeah, yeah, wavelength into kind of yeah wave numbers, okay. So that's yeah very easy math, okay. So we get here the yeah wave number range, okay, for the yeah IR should be from yeah 4,000 per centimeter to 400 per centimeter, okay. So yeah, that's here means yeah the higher end kind of yeah the 4,000 kind of yeah waves in 1 centimeter. Here kind of yeah the 400 yeah, waves in 1 centimeters. So the actual number kind of yeah easy to write, easy to remember. Okay, so yeah. All right. So for the bound vibration, actually there are 2 types of yeah bound vibration. One's called stretching, one's kind of called bending. Okay, the stretching just like this way. Okay, so I go back and forth. Okay. Bending kind of like this way. Okay, so yeah, just kind of yeah shake. Okay. So each vibrational bond occurs at kind of a certain yeah, frequency. Okay. So if a molecule can absorb IR, if the frequency of the IR equals to kind of frequency of a particular kind of the bound vibration, okay, and then you see kind of the UV IR peak. Okay. So yeah, there's kind of yeah peak signals. Okay. Absorption peaks. Okay. And but yeah, yeah, for the same kind of bond, okay, so yeah, yeah, normally speaking, kind of yeah, for same bond you can do the stretching or kind of yeah waving case, so yeah, bending case, so yeah, but yeah, stretching normally causes large kind of dipole moment change case, so yeah, and then has higher frequency, and then yeah, than the yeah bending case, so yeah, shows kind of higher frequency. So what's that mean? Okay, we kind of yeah one easy example. Okay, so yeah, for example, water. Okay. And so we know that kind of water has the bend structure, okay, like this, okay. So water has yeah some dipole moment, okay. So yeah, partial negative charge on oxygen, partial positive charge on hydrogen, okay. Dipole moment yeah should like this. Yeah, all right, okay. So if the stretching happened, okay. So for example, okay, so yeah, that's stretching, okay, go like this way, and then yeah, you find the yeah bigger kind of the yeah dipole moment change. Okay, so here still partial negative, partial positive, okay. And then yeah, the dipole moment change kind of feel the bigger. Okay, yeah. So this we call stretching. Okay, and yeah, so when water do the bending, okay, so yeah, bending okay something like this, right? And then yeah, once water do the bending, okay, so yeah, that's yeah something generally like this. still partial negative, partial positive, partial positive. Okay. So you find the kind of for the bending case, so the dipole moment change kind of not too much. Okay, so that's still dipole moment like this. Okay, so that's why kind of the stretching case, so normally the give you the higher frequency case, so close to 4,000 kind of per centimeter kind of range, and then bending kind of low frequency, close kind of 400 kind of the wave numbers. Okay. All right. And for the stretching, actually kind of there's more than one kind of stretching case. So two main kinds of stretching case. So one is the C stretching case, C stretching kind of like this. Okay, so like this. Okay. One is the unsymmetrical kind of one's kind of symmetrical the stretching, one's kind of unsymmetrical stretching. Unsymmetrical stretching, one bond going this way, one bond going this way. Okay, so that's unsymmetrical stretching. Okay. And then for bending, there are also many types of bending. Okay, so here at least two. Okay, so one's kind of in-plane bending, another called kind of auto-plane bending. There's also kind of called rocking, twist, kind of rocking, something like this. Okay. So in this case, you can see, okay, even for one bond, okay, so they kind of the CH bond, okay, so we can have many different the stretching and also many different kind of bending. Okay. So that's why each of them may absorb some IR frequency. Okay. So that's why IR spectrum is very complicated. Okay, because even one single bond. Okay, so you can have kind of the different bending, kind of the stretching. Okay, so that's you can have the different the IR signals. Okay, very complicated. All right, and here come to a relatively important point. Okay, so not all the atom, okay, not all the molecule are IR active. Okay, so you can use IR to show their kind of spectrum. Okay, so not all of them. Okay, so the molecule. Okay, so when the vibration occurs, okay, have to make sure there's kind of dipole moment change. Okay, then you can have IR signals. Okay, so like here, okay, the water. Okay, so dipole moment change. Okay, you have IR signal. Okay. And so that's shown here. Okay, so band kind of stretch. Okay, so the increasing distance between atoms increase the dipole moment. Okay, so that's shown here. Okay, and normally speaking, okay, so for the molecule, if you have kind of the more polar bond, okay, and then you get kind of higher intensity the absorption. Okay, so later I will show you kind of the OH IR spectrum and also NH IR spectrum and CH IR spectrum. You can see clearly. Okay, OH has kind of a bigger peak than NH, and kind of NH bigger than CH. Okay, because the OH kind of more polar than NH, and followed by kind of CH. CH is pretty much non-polar. Okay, so and so imposing kind of like I said, okay, not molecule, okay, not all the molecule can have IR spectrum. Okay, because some molecule, for example, just the non-polar molecule. Okay, then there's no dipole. There's definitely no dipole change. Okay, so even you have kind of bond stretch. Okay, so for example, we have kind of chlorine molecule. Okay, chlorine molecule like this. Okay, the whole molecule is just the non-polar. Okay, so no matter how do you do stretching, no dipole moment change. Okay, same thing for the oxygen molecule. Okay, so no matter how do you do the stretching, okay, how do you bending, okay, so there's no dipole moment change. Okay, so those no IR. Okay, so no IR, no IR. Okay. And then for polar molecule or kind of polar bond, okay, so it's also not necessarily has the IR absorption. Okay, you have to make sure that the dipole moment change. Okay, when the vibrations stretching bending happen. Okay, so give you one example. Okay, carbon dioxide. Okay. Carbon dioxide. Okay, so there's the CO double bond the polar bond. Okay, and then partial positive on the carbon, partial negative on the oxygen. Okay, all right, and then if you do the symmetrical stretching like this, all right, and then we can draw the symmetrical stretching kind of the carbon dioxide kind of molecule after stretching. Oxygen, all right, still partial positive on carbon, partial negative charge on oxygen. Okay, So then you'll find that there's no dipole moment change for this the symmetrical strategy. Okay. So because the center of dipole moment is still here, okay, on the middle of the carbon. Okay, so here, okay, no dipole moment change. Okay. So that means here the symmetrical strategy for the carbon dioxide, no IR absorption. Okay. But if you do the unsymmetrical strategy in case like this, that's unsymmetrical strategy. Okay. Then there will be a dipole moment change. Okay. So Right. Okay. So now next positive charge still on carbon, next charge on oxygen. Okay. So now you see kind of the very beginning case. So the center of the next charge, positive charge in the middle of the molecule. Okay. Now kind of not overlap. Okay. There's a dipole moment change. Okay. So there's dipole moment change. There will be IR absorption. Okay. So those please keep in mind. Okay. So have to get dipole moment change, and then you can see the IR signal. Okay. And then next to come to the for all the different bond case, so different bond case, so they have a different the IR absorption case, so because they have a different the energy, different frequency case, so then this case they have kind of a different position to absorb the IR absorption case. So here I give you guys kind of one formula case, so that's explain the bottom kind of the easy case. So this formula is not in your textbook, but I think kind of relatively good for you understand the different energy, also kind of different bond, and then different mass, influence to the IR absorption, here, So that's the formula, So the K here, So K is the we call the force constant, And then I'm here is the mass. And mass case force constant. Right. So force constant is kind of how strong of the bond. So clearly is you can see kind of if you have higher K, higher the force constant, and then you have higher frequency. K is higher, and then you have higher frequency K. Right. And then for the mass, so you can see clearly so if the mass is higher, so the frequency will be lower, because there's kind of underneath of this line, Right, and then now we can come back here, So explain some kind of observation, So first kind of bond strength, The stronger the bond, stronger bond, and then you have higher K, and then you have higher frequency, So higher kind of the IR frequency absorption, So that's explained here, So normally speaking, kind of the CC2 bond, has higher frequency than CC bond, and then higher frequency than CC single bond. You understand, because the CC2 bond, the stronger bonds, so the closer distance, so higher K and higher frequency. And similar thing for the CO bond and also CO single bond, CO bond higher frequency than CO single bond, So those please keep in mind, And then that's here. Stronger bond require more energy to stretch, and then higher frequency, And then come to mass of the atom, So from here we understand the higher the mass and then lower frequency, So that's true for the IR absorption, So example showed here, So for the bond we have CH, CO, CBr, So the hydrogen has the lowest kind of the mass, and then has highest frequency, and then followed by CO, and then followed by CBr, So in other words, lighter atom vibrate at higher frequency. Lighter atom at the higher frequency. To help you guys kind of visualize it, so get here one YouTube video, This one just use spring and also different mass, So to see the frequency, So
demonstration, we will show the effects of variable mass. Note that as mass increases, the natural frequency of the spring mass system decreases.
All right, we do it again, All right.
First demonstration, we will show the effects of variable mass.
All right. So for the left one, so it has a lower mass. Middle one has kind of the medium mass, and then right one, you can see kind of a lot of the weight on it, so a higher mass, And then they use same spring, and you just take close look here. What's the other kind of frequency?
Note that as mass increases, the natural frequency of the spring mass
you can see kind of
decreases.
Small mass has kind of a higher frequency, and then the higher mass kind of the lower frequency. Okay, that's also explained here. Okay, so lower lighter atom. Okay, so will give kind of higher frequency, and then the higher atom will get kind of lower frequency. Okay, so those please keep in mind. Okay. And in the end, okay, so come to the hybridization of the carbon. Okay, so that's actually kind of pretty interesting. Okay. So normally speaking, okay, so the sp hybridized carbon. Okay, so and then it's build bond with the hydrogen. Okay, has higher frequency than the sp2 hybridized carbon with hydrogen. Okay, and then lowest one is sp3 hybridized the carbon hydrogen. Okay, so reason for that is still related to K. Okay, so we call it the force constant. Okay, so carbon is sp hybridized. Okay, so they have kind of more ice factor. Okay, so how kind of higher electronegativity. Okay, higher electronegativity. Okay, absorb the kind of hydrogen close to the carbon, and then shorter bond, and then stronger bond, and then stronger bond. Okay, and then higher kind of force constant, and then higher vibration kind of Okay, so that's why the wave number of the ICP hybridized carbon H. Okay, so 3,300 okay per centimeter. Okay, and then followed by the sp2 hybridized kind of CH. Okay, and then saturated the CH. Okay, so this kind of lowest kind of frequency. Okay, so for this case. Okay, and for you guys here, just please remember. Okay, so pretty much in this order. Okay, so for the alkyne CH. Okay, so we refer to here. Okay, so this one. Okay, higher frequency than alkene CH. Okay, and then lowest one to the alkane. Okay, so so here we just compare the alkyne CH, alkene CH, and also saturated kind of CH. Okay, here just keep in mind. Okay, right. Here's the setup of the IR spectrometer. Okay, so also called spectrophotometer. Okay, so there kind of the light resource. Okay, and then you let it pass through the monochrometer. Okay, so that's the spread out all the wavelengths kind of light. Okay, and then let this the different wavelengths light pass through slit. Okay, and that's the sample cell. Okay, so if there's sample will absorb certain wavelengths of the IR. Okay, and then you see kind of absorption peak. Okay, so this can be detected by detector. Okay, so nowadays kind of IR kind of pretty instrument kind of pretty cheap, also kind of pretty modern. Okay, so in probably lab 6. Okay, so we will learn how to record IR. Okay, and IR can also make pretty small. Okay, like this handheld kind of IR instrument. Okay, pretty kind of cool. Okay. Right, and then here's kind of the IR spectrum. Spectrometry spectrum. Okay, IR spectrum. Okay. So that's real IR spectrum. Okay, so for IR spectrum. Okay, so the y-axis we call the y-axis kind of we call the transmission transmittance. Okay, percentage. Okay, so that's actually kind of just the absorption. Okay, so transmittance. So if we see the zero absorption, that will be 100% the transmission. Okay, so that's 100. Okay, and if we see the 100% the absorption. Okay, so then will be zero transmission. Okay, so that's here. Okay, right, and then for the x-axis is just the wavelength. Okay, so wavelength. Okay, so sorry, should be the wave numbers. Okay, so we use the wave number as the units. Okay, so 4,000. Okay, so per centimeter on the kind of high frequency end, and then another end kind of low frequency. Okay, 400. Okay, and then for IR. Okay, so that's the some kind of unit you will see here. Okay, and then if there's no the absorption, will show kind of line close to 100. Okay, and if there's absorption. Okay, so show like this. Yeah, something like this. Okay. And so that's here is real kind of here the IR spectrum showed you guys here. Okay. And then by read through here the wave numbers. Okay. You interpret kind of here there's here the 240 kind of 200 2400 kind of nanometer per centimeter peaks. Okay. And so also showed here. Okay. So absorption band. Okay. So also we call the absorption band. Okay. So that's here appear kind of some kind of the IR absorptions. Okay. So and then y-axis, x-axis. Okay. And quite often people label the IR band as kind of W. Okay. So indicate weak. Okay. So so that's similar. Like this peak is kind of pretty weak. Okay. And then use M indicate this kind of medium kind of peak. Okay. So medium. Okay. So and use S indicate is strong the peak. Okay. So strong absorption. Okay. So that's strong S, medium M, weak kind of W. Okay. And then when you read some literature, quite often people report some kind of compound the IR spectrum. Okay. So list kind of the wave numbers. Okay. For example, kind of 2451 okay per centimeter. In then okay. So quite often put some kind of the letter after this wavelengths. Okay. Wave numbers. Okay. So like S or kind of M or W. Okay. So that's indicate how strong this signal. Okay. So S means strong, medium means kind of medium. Okay. And weak means weak. All right, okay. I guess that's we done the today's class. Okay, so we continue IR in the class on Friday. Okay, Friday we still have class. Okay, so right. Any questions? You too. Okay, have a good day. Thank you. So I have office hour from 3 to 5 today. Okay, so if you guys have questions, okay, need help for the exam too. Okay, please come at 3 to 5. Okay, and otherwise, okay, have a good day, everyone.